Recall the equation of the normal distribution, where mu is the mean of the distribution and sigma is the standard deviation. X is the independent variable and y is the dependent variable. A special case of the normal distribution is when mu equals 0 and sigma equals 1. It is a special case of the normal distribution and is called the standard normal distribution. It has all the same properties of any other normal distribution, including a cumulative distribution that behaves the same way as any other cumulative distribution. It approaches 0 when x becomes much less than the mean, in this case negative values, and approaches 1 as x values get much larger than the mean. As we learned earlier, the way to find the area under the normal distribution is the cumulative distribution. Unfortunately, we do not have an equation for the cumulative distribution. We have an equation for the normal distribution, but for reasons beyond the scope of this discussion, there is no equation for the cumulative distribution. This is why we need to resort to a special case of the standard normal distribution. The cumulative distribution of the standard normal distribution is solved once graphically, and these values are saved in a table. We will then be able to make use of this table for any normal distribution, and we will see how shortly. Let's first see how the table works. The values on the horizontal axis for the standard normal distribution are known as z-scores to differentiate it from a normal distribution. The table is generally divided into positive and negative z-score values. The negative values are values to the left of 0. The z-scores shown on the horizontal axis are the first column and the top row of the chart. The positive values are also part of the table, and we will describe them in a moment. For example, a z-score of minus 1.25 is separated into minus 1.2 to include the first digit to the right of the decimal, and 0.05 for the second digit to the right of the decimal. At the intersection of this row and column, we get a value of 0.1056 for the area to the left of minus 1.25. This part of the table will give the area for the left half of the standard normal distribution curve. For values greater than 0, we refer to the positive z-score table. For example, a z-score of 1.25 is separated into 1.2 for the first digit to the right of the decimal and 0.05 for the second digit to the right of the decimal, for an area of 0.8944 to the left of a z-score of 1.25. The positive z-score table gives the area under the standard normal distribution for z-score values greater than 0. Let's look at the normal distribution and determine some probabilities using the z-score table. The distribution for this example has a mean equal to 100 and a standard deviation of 20. We will determine the probability of a random variable falling between the values of 80 and 110. We will start by finding the probability of x being less than 80, which is the area under the normal distribution to the left of the value 80, and is equal to the value of the cumulative distribution at the value 80. Recall the relative standing equation from an earlier video. It is used to calculate the position of the x value relative to the standard normal distribution. Therefore, the z-score for x1 is 80, the value of x1, minus 100, the value of mu, divided by 20, the value of sigma, for a result of minus 1. The relative standing of 80 is minus 1. The probability of z being less than minus 1 in the standard normal distribution has the same value as the probability of x being less than 80 in the normal distribution, which has a mean of 100 and a standard deviation of 20. The z-score should now be thought of as the number of standard deviations the random variable is from the mean. Notice that the distance x is from the mean is 20, which is the same value as the standard deviation. Therefore, 80 is one standard deviation less than the mean. When plotted on the standard normal distribution, a z-score of minus 1 has the same area to its left as did the 80 on the normal distribution. We now look up the area to the left of a z-score of minus 1 in the table. The area to the left of z equals -1 is shown here. In the left column we find -1.0 for the first digit to the right of the decimal. In the top row we find 0.00 for the second digit to the right of the decimal, which indicates an area of 0.1587 to the left of -1. So the probability of z being less than -1 is 0.1587 and is the area to the left of -1. Switching back to the normal distribution we started with, we notice the area to the left of 80 is the same. Therefore, the probability of x being less than 80 is also 0.1587. Let's now determine the probability of x being less than x2, where x2 equals 110 for this example, and is equal to the area to the left of 110. This area is equal to the value of the cumulative distribution as x2 equals 110. The next step is to calculate the z-score of 110 as we did for the value 80. The z-score for x2 is 110, the value of x2, minus 100, the value of mu, divided by 20, the value of sigma, for a result of 0.50 for the z-score. The relative standing of 110 for this distribution is 0.5. An x value of 110 in the normal distribution has, in the standard normal distribution, the same area to its left as 0.5, its relative standing. It is this value we use to look up the area to the left. At z equals 0.50, the area to the left is 0.6915. That means the probability of z being less than 0.5 in the standard normal distribution is 0.6915 and has the same area to its left on the standard normal distribution as 110 has to its left in the normal distribution, making the probability of x being less than 100 also 0.6915. It then follows that the area between 80 and 110 is the difference between 0.6915 and 0.1587, which is 0.5328, and is the probability of x being between 80 and 110.